Section 7.9, Impulses and the Dirac Delta. In this section, we want to investigate and model systems with sudden spikes of input energy, for example, a hammer strike in a mechanical system or a voltage surge in a circuit. So to accomplish that, we first want to introduce the concept of the Dirac delta, sometimes called the Dirac delta function, even though it's not a function. But the Dirac delta, denoted by delta of t, is defined by the two properties. Number one, delta of t is 0 when t is not 0, and it has the value of infinity exactly at t equals 0. So you can visualize this is just a heuristic. This is not really the graph of a function, but it's a heuristic you can think of on the entire t-axis. The graph of delta of t is at 0, and then exactly at the 1.0, it has an infinite spike up to a height of positive infinity. So that's one property. And the second property that we want from the Dirac delta is that if you integrate from minus infinity to the infinity of the Dirac delta times a function f of t, and you integrate across all time, that the result of that will just be the function value at 0. So right now you might not have a good feel for where these two defining properties came from, but we're going to take them as the definition of the Dirac delta and see what we can get from these concepts. So more generally, we might want a Dirac delta that doesn't have the spike occurring at t equals 0, but rather it occurs at, say, t equals a. And so we can just think of that as a shifted version of the standard Dirac delta. And so you can think of delta of t minus a is just a delta that's been shifted to occur at t equals a. So now the graph looks like this. The function is still 0 everywhere except when t is equal to a, and exactly at a there's an infinite spike. So this is just a shifted Dirac delta. And then secondly, if you shift the Dirac delta, the concept of 2 is still in play, which means if you take a delta whose spike occurs at a, you multiply it by a function and you integrate, you're going to pick up the function's value at the time where the spike occurs. So here the spike occurred at 0, so we picked up f of 0 as a result of the multiplication and integration. And here the spike occurs at a, so when we multiply f of t and integrate, we're going to pick up f of a. And this is sometimes called the sifting property of the Dirac delta, that when you take a function, multiply by a Dirac delta, and integrate over all time, you're going to sift out or throw away all the function values of f except for the function value at the time when the spike occurred. Now the motivation for this is that if you recall from physics that the impulse due to a force that is applied over a time interval from a to b, so big F of t will be our force, it's applied over a time interval from a to b, the impulse due to that force is just the integral of that force over the time interval. And if force is mass times acceleration, and the force we were going to look over the impulse over an interval from a to b, that would be our force is mass times acceleration. We want to calculate its impulse. We would just integrate from a to b, mass times acceleration. Acceleration is the first derivative of velocity, so we have this. And now we anti-differentiate this with respect to t. Remember, mass is constant. So this is just v of t evaluated from a to b. When we evaluate, we get mass times the change in velocity. And if you remember, mv is just momentum. So this is just the change in momentum over the interval from a to b. That gives us a very concrete realization of or interpretation of what the impulse due to a force is over an interval. It's just the change in momentum over that interval. And so another way that you can think about and where this is leading to in terms of Dirac delta is if you think of, for example, I have a force. I'm going to apply this force over an interval from a to b. Maybe I'm pushing on a box or something like that to create a force. And now if I just, as a simple diagram, I think of it as a constant force. Then over time, I apply this constant force. And so now integrating that force over the interval, the area under the force curve is just the impulse, and the impulse is the change in momentum. So when I do this, where this area is 1, we call that a unit impulse or a unit change in momentum. So a way to accomplish that would be that if we're applying our force on some interval from a to b, then we'll just take our force to be 1 over b minus a, and then the base times the height. This will give us an area of 1, and this unit impulse is a consequence of having a 1 unit change in momentum. So those two things go hand in hand. So now imagine we take the same graph that we have here, and we just shrink the interval from A to B. We make A move to the right, and we make B move to the left. So what we're doing is we're taking the same force, 1 over B minus A here, and we're just applying it on a shorter and shorter interval. So we can see that if we're going to maintain the same amount of area, so we want to maintain a unit impulse, a unit change in momentum, that if we shrink this interval length, we have to be increasing our force because B minus A gets smaller, so 1 over B minus A gets larger. I know I've drawn these on the same scale, but actually this would be a lot taller version of a rectangle here, and then if we shrunk A and B even more, then what's happening is this unit impulse is giving us a sequence of these boxes that are getting taller and taller and skinnier, and then in the limit, as B minus A goes to 0, as this width goes to 0, this height must be going to infinity, and in the limit you would get the idealized Dirac delta, which is an infinite spike that would represent a unit impulse or a unit change in momentum that's occurring exactly at the point t naught. So this is the motivation for a Dirac delta. Just think of it as a limit of playing this game with these unit impulses, as the time interval over which the force is applied is going to 0 but never actually reaches 0. Now, once we have this new Dirac delta in our repertoire, since we're here in this chapter studying Laplace transforms, it's very natural to say, hey, how do we take the Laplace transform of a delta, of a Dirac delta? Well, the Laplace transform of delta of t minus a, let's just go with the integral definition and calculate it. This would be from the integral definition of the Laplace transform, the integral from 0 to infinity of e to the minus st times delta of t minus a dt. And you might think when you just look at this that this will be a very complicated integral to compute because this is a very unusual type function. But actually, due to the sifting property, this is one of the easiest integrals you'll compute. Because remember, due to the sifting property said that if you have a delta whose spike occurs at time a, and you multiply and integrate, you're only going to pick up that function's value. The result of the integral will be that function's value at the time where the spike occurred. So by the sifting property, this is going to reduce to just e to the minus st, evaluated at the time when the spike occurred at t equals a. It's very important. This is t equals a, not s equals a. And so when we do this, we get e to the minus as, and now we can highlight this. We have a new table entry. The Laplace transform of delta of t minus a is e to the minus as. Now, let's put this to work for us in an example. So in our textbook, they refer to these as symbolic initial value problems because this isn't really a function. This is really more of an idea in our head. But if you think of this as being the spring mass system, and you think of this as the forcing function, then what's happening here is we have a mass of 1, we have no damping, and we have a spring constant of 1. And then our forcing function, remember, this is a delta that's occurring at time 2. So there's going to be an instantaneous unit change in momentum, or an instantaneous unit impulse, and it occurs at time 2. So we would think of this as something like a hammer strike in a spring mass system. You have your mass on the end of the slinky, and instead of moving your hand or the platform that the spring is attached to, we're going to walk along and do nothing to it, and then at time 2, we're going to strike it. And now how hard do we strike it? We strike it enough to result in a unit impulse. If this was a 3 here, then this would be a 3-unit change in momentum. If it was a 22, it would be a 22-unit change in momentum. Right here we have a 1, so it would be a 1-unit change in momentum, and it's going to occur at time 2. And let's go ahead and give initial conditions where the mass was initially at rest. No initial displacement, no initial velocity. So how would we solve this symbolic initial value problem? I call it a hammer strike problem. Then we would just take the Laplace transform of both sides. This is very familiar to us. We apply our theorems to work out the left-hand side. We know how to do that from the past. And now with our newly found table entry, we know that the Laplace transform of delta of t minus 2 is just e to the minus 2s. We apply our initial conditions. We factor out our big Y of s. The right-hand side just is what it is. We isolate big Y of s. We take the inverse Laplace transform of both sides. We know how this inverse transforms. To inverse transform this, we need to use our available theory and table. And so I think the way to look at this is let's peel off this e to the minus 2s, and let's view this as an e to the minus as times a big F of s that we know how to inverse Laplace transform. So we go back to our theory, and we had this table entry, which if you read this from right to left instead of from left to right, this tells us that the inverse Laplace transform of this is this. So we just need to identify our A, identify our big F, know what our little f of t, what this inverse transforms back to, and then apply our theorem. This is the inverse transform of this will be little f of t minus 2 times u of t minus 2. Little f in this case is sine t, so this would be a sine of t minus 2 times u of t minus 2. And if you think about what this function represents, this is a switch that kicks on at time 2. Before that it's off, so it gives a value of 0. After time 2, it kicks on this function. And so the response of, say, this mechanical system, when we have this, it's initially at rest, no initial displacement, no initial velocity. We're going to walk along and impart a 1 unit change of momentum instantaneously at time 2. Then what's going to happen? The mass was just sitting there, sitting there, sitting there. The hammer strike occurs at time 2, and now it starts to oscillate. And it continues to oscillate because notice there's no y prime term here, so there's no damping. This is an undamped oscillator. It just oscillates forevermore, and it's purely sinusoidal. So all of that makes sense, and we see that we have put to work calculating the Laplace transform of our Dirac delta to help us solve these hammer strike problems, or you can think voltage surge problems, these kinds of things that need an instantaneous input of energy into the system. Now, another approach that can be used to handle these types of things, if you remember above, we got to this stage and we used our previous theorem to calculate this, and that's all well and good. It's totally fine. I want to show you a different perspective because sometimes this comes into play and you may prefer it, or it may be the only methodology that will get it done for you. In this particular problem, we know how to do this different ways, but I want to expand your horizons. Instead of using our theorem that we did last time, let's view this based on the convolution theorem that we just talked about in the last section. Let's view this as we need to calculate the inverse Laplace transform of a big F of s times a big G of s with regular multiplication in the s domain. Now the key is, if we know how to inverse transform the individual pieces, and now we do, this individually inverse transforms back to delta of t minus 2. This individually transforms back to sine t. We've known that for quite a while. So we know what the corresponding little f of t and little g of t are. So by the convolution theorem, we can invert this product in the s domain to become the convolution product of little f and little g in the t domain. And that might look intimidating at first, but notice this was very quick. We almost got this immediately. And now it's just a matter of if we can handle this convolution multiplication. Well, one of my pro tips here is when you end up with a convolution involving a delta, put the delta, since we know our convolution product is commutative, we can swap the order of these when they're multiplied. We have the freedom to rewrite this in this form using commutativity. It's always going to be easier. The little pro tip here is to put the delta on the back end of the multiplication. And you're going to see why in just a second. And now let's compute this convolution product as an integral. When we compute this convolution product as an integral, remember the definition is we're going to integrate from 0 to t of our f of t minus s. This is my f of t, so f of t minus s, regular times my g of s, this is g of s, ds. And now you might say, well, I don't know if that's any better or worse because I'm multiplying by a Dirac delta and I'm not comfortable with that, and I'm integrating that. But let's just pause for a second and reflect on what's going on here. Think of the s is varying from 0 to t. So for right now, just think of t as fixed. S, for whatever t is fixed at, s is going to vary from 0 to that fixed t. Now there's two cases here. Here our s is going to vary from 0 to t, and there's two cases. Either my big T that I've fixed is before 2 or it's after 2. I don't know in this situation either. I don't know what T you have in mind. Maybe the T that you have in mind is 1.5, or maybe the T you have in mind is 17. I don't know. So there's two cases. If T is less than 2, then think about if T is smaller than 2, you have not integrated across this spike. When S goes from 0 to T, if T is to the left of 2, then the S never went across this delta spike. Since it never went across this delta spike, this is a big zero because this function is just a big zero and you never integrated across the spike, so the sifting property never kicked in. So if t is less than 2, this function is 0, so the integral of it has to be 0 if t is less than 2. On the other hand, if t is greater than or equal to 2, then that means S is going to travel across where the spike occurs. It's going to integrate across the spike. And when you integrate across the spike, the sifting property tells you how the story ends. It says if you multiply against a delta and you integrate across the spike, you just get the function evaluated at the place where the spike occurred. And here the spike, this is with respect to the S variable, not the t variable. And so we would just get, when you apply the sifting property, if t is greater than or equal to 2, you get our function sine of t minus s evaluated at the place in the S variable where the spike occurred. And that will be true for t. You can say greater than 2 or greater than or equal to. It doesn't matter. We're never quibbling over what exactly happens at 2. And so then this simplifies to this. And notice that this you could rewrite in terms of unit steps as just this. And this is exactly the answer that we got above. And so you might want to think about trying this both ways when you use a convolution with a delta. There are many, the reason I'm showing you this is there are many places in mechanical engineering, electrical engineering, especially signal processing and physics, to where you will encounter, once you've had this course, you will encounter convolution products or convolution integrals that involve a delta, and this is giving you a preview of how you can handle them. As long as you just interpret them correctly, think about them like this can be a very nice tool to have in your toolbox to compute those things. Okay, as another example, let's go back to some of the things we were talking about in the last section, and let's find the impulse response function for the system, y double prime plus 6y prime plus 5y equals delta t. So this would be a unit impulse that occurs at time 0. Unit because it's a 1. It applies at time 0 because that's the place where the spike occurs. And we'll have the system initially at rest because that's what we need to do to find, well, we were going to do that anyway to find transfer functions and impulse response functions, but here's our system. So remember that the transfer function associated with these systems, you needed to have rest initial conditions, and we do. It's just 1 over the characteristic polynomial. And so if you do, I don't show the details here, but if you do this partial fraction decomposition, this is what you'll get. And so to get the impulse response function, little h of t, I want to find the transfer function, and then I want to inverse Laplace transform it. So the impulse response function is the inverse Laplace transform of this stuff. And now, after I've done the partial fractions, I can just pull out the 1/4, and each of these is very simple to do. So I have the impulse response function. Okay, so that's fine. Notice we've just found an impulse response function for a system that has a delta in it. But notice that here, what the forcing function is has no bearing on finding the transfer function or the impulse response function. So where am I going with this? On the other hand, I want you to look at, suppose we were to just solve this, not ask for the impulse response function, but solve this differential equation with initial conditions, this initial value problem. Okay, we'll play along with me. We'll just take the Laplace transform of both sides. We'll apply our standard techniques. We'll use our differentiation theorems. Notice on the right-hand side, the Laplace transform of the delta of t is very easy. It's just 1. Since we had rest initial conditions, these all zero out. So we get this. When we isolate for big Y of s, when we inverse transform, we get this. And now we already calculated the inverse transform of this. We just did it above, right here. We just did it. So the inverse transform of this is this. And so what's going on here? I did this to show you why, and I never explained this in the previous section. Why do we call this the impulse response function? Why do we call this guy the impulse response function for this? Why did we ever call it an impulse response function? It's because when your forcing function is a impulse, it is a unit, it is a Dirac delta with a unit impulse with a change in momentum that's occurring exactly at 0. So when your input is this unit impulse, then what's happening is the solution to that system is the impulse response function. That's where it gets its name. It's the response of the system to a unit impulse. This is the impulse response function. It's the solution to the system in response to a unit impulse. That's why it gets its name. And so the punchline here is that the impulse response function, little h of t, defined by the inverse Laplace transform of the transfer function, is in fact actually a solution to the system when your input is a unit impulse, is delta of t with rest initial conditions. Now, of course, you might have input functions that are other things, sines, cosines, square roots, squares, it doesn't matter. But when it's a delta, it turns out that the little h of t is not just this function that's associated with the system, but it's actually a solution to the system. And that's where it gets its name of an impulse response function.